Welcome to qnawire.
Okay, so this is another two-dimensional vector decomposition problem, and I will try my best to redraw the diagram, the figure that's given in the textbook, E4.3. So basically what's going on is that we have a patient wearing a chin strap that looks a little something like this. So it's pulling on him in these two diagonal directions, and then it catches up to these little wheels that come back around and make kind of a diamond shape. And they meet back in the center, and they're pulling upwards. So again, there's a little rotational wheel here, and another rotational wheel here, and then a key piece of information that's only given in the figure is that the angle in between these two straps is the angle theta, which is 75.0 degrees in this problem. We'll need that number in order to numerically solve the problem. That's 75.0 degrees. Okay, so that's great. We have an upward left force and an upward right force. And then really importantly is that we're not actually going to be using the angle theta, so which is the angle theta over 2 in this problem, because there's a line of symmetry going down the bottom. So let's use the head to tail method for vectors in order to put them from head to tail. So let's do the left vector first and then the right vector second. So we know that it's symmetric, so they're going to be the same magnitude. And then if we do it like this, they will end up with a perfectly straight up vector. Let's call that F tote. And then again, they're two equal and opposite. They're two equal but not necessarily opposite vectors. So we'll call them T for tension. One in the upward left direction and the other one in the upward right direction. Their angle theta over 2 is sneakily hiding over here in this corner as well as this upper corner. So we have another natural line of symmetry, and that is the horizontal one going right here to show that we have a nice right angle between the horizontal axis and our F tote vector. So now would be a good time to define a coordinate system, that being X in the horizontal direction, just a classic coordinate system, and then Y going upward in that vertical direction. So let's start translating free body diagrams into actual equations. We're going to want to use the cosine trigonometric function for the tension vector because we're interested in the vertical component, we're interested in the y component, so that's going to be adjacent over hypotenuse. So, and this is true for both tension vectors. We're going to get the cosine, and then remember it's going to be of theta divided by 2, not just theta. Awesome. So as we described earlier, the total vector is going to be purely in the vertical direction. And then again, we have symmetry here where the two tension vectors are the same. So it's literally just going to be the y component twice, one contribution from left and right. So now we can go ahead and add this together. So you get a nice factor of 2. Substitute in the relationship that we just found. Nice theta over 2. But then remember, we're solving for t, so we're going to have to rearrange this. F tote is technically given to us. That's given to us in the form of 5.00 newtons. So do some algebraic gymnastics in order to isolate t, put everything else on the other side of the equation, top it all off with F tote, and then that is what our answer looks like in variables. We can go ahead and plug in some numbers. Let's do the last step. Sorry, that's supposed to be a 5.0 newtons. And then on the bottom, 2 cosine 70, oops, 75.0 over 2, 75.0 degrees over 2, and then to, running out of space here, but let's go left. To 3 significant figures, that's going to be 3.15 newtons. Don't forget the units. Put a nice big box around that. Okay, and then we are all done.